Thank you. Yes, thank you very much.
Question number one is asking to make a table, right?
Yeah?
So this is one table putting all this data and
No,
sorry about
and
that.
we're starting our lesson now, so maybe you can talk to me afterwards. Okay. Okay, so we're going to be starting our lesson. You're going to be writing 2 conversion factors related to the mole. We're going to do this every day until your mole quiz. So for those of you sitting there with no pen or writing implement or anything to write on, you need to get something with which to write and something to write on, and you need to write down 2 conversion factors related to the mole. Elijah, what are they? Okay, a number over 1 mole. Okay, so I'm going to put 1 mole on one side. And you know why I asked you, right? Yeah, okay. Yeah. 6.02 times 10 to the 23. And this is going to be 1 mole of usually particles. I don't know why I didn't leave enough room for that. Silly me. And that is equal to 6.02 times 10 to the 23 particles. And if you have trouble remembering whether the 6.02 times 10 to the 23 goes with the particles or whether it goes with the moles, remember you have 1 little mole at the front. I should get myself a mole costume. That would be awesome. If anyone is clever at sewing and wants to make me a mole costume, I would pay for the materials. Okay, anyway. So we have 1 mole of particles equals 6.02 times 10 to the 23 particles. Whose number is this? Avogadro's number. Okay, that is our first conversion factor related to the mole. Tell your partner, what is the second one? It is the particle ratio, yes. And it could be any number of things, but it's going to be the number of particles of type A to the number of particles of type B. And how do we find that number? We look at the formula. So for example, if we have water, we could, for example, have 2 H atoms per 1 H2O molecule. Okay, so today what we're going to do is we're going to look at the mole ratio, which is very similar to the particle ratio in that the numbers are the same, we just change the units. So we're actually going to go to think it's is it page 24? Page 24, 5.1i. On page 24. So the mole ratio is the same as the particle ratio, but it includes the unit mole. So if we have a molecule of dinitrogen tetroxide, you can see that we have 1, 2 nitrogen atoms, yes? Okay, so we have 2 nitrogen atoms in the 1 N2O4 molecules. We have a 2-to-1 ratio. That's our particle ratio. Now, what if I were to scale this up a little bit? And what if I gave you 1 pair of N2O4 molecules? In other words, 2 N2O4 molecules. How many pairs of nitrogen atoms do I have? Well, we've got 1 pair of nitrogen atoms in the first molecule, another pair of nitrogen atoms in the second molecule. So we have 2 pairs of nitrogen atoms. So the number is staying the same. I've got 2 pairs of N atoms in 1 pair of the N2O4 molecules. The only thing that has changed is now we have added the word pairs. And of course, with any of these, we can turn them upside down if we need to. Now, if I have a dozen N2O4 molecules, and you can count them up, in the first row we have 1, 2, 3, 4, 5, 6 molecules, and in the next row we have our 7, 8, 9, 10, 11, 12 molecules. So we have 1 dozen, we have 12 NO2s. So in other words, N2O4s rather, we have 1 dozen N2O4s here. Then if we count our N atoms, we have 2, 4, 6, 8, 10, 12. So in our first row, we have 12 N atoms. And in our second row, we will also have 12 N atoms, which is equal to 24 N atoms, which is equal to 2 dozen N atoms. So once again, we have 1 dozen molecules contain 2 dozen N atoms. Yes? So we still have a 1-to-2 ratio. We've just added the word dozen. Now, I did not draw out a mole of the molecules because, you know, not enough paper, right? But if you have 1 mole of N2O4, you're going to have 2 moles of N atoms. So once again, we have a 2-to-1 ratio. And this one is called not the particle ratio, but it is called the mole ratio. But the numbers are the same as the particle ratio. Okay. Let's find another mole ratio. In nitrogen dioxide, if you have 2 N atoms, that means you have 1, 2, 3, 4 O atoms. So we have a 2 N atoms to 4 O atoms ratio. That's our particle ratio. 2 to 4. 2 N's to 4 O's. Two to 4. Now, if we double everything and I give you pairs of N2O4 molecules, you can see here we've got in the little dashed circles, we have 2 pairs of N atoms, yes, that's 4 N atoms in total. And then we have 1 pair of O's, 2 pairs of O's, 3 pairs of O's, and 4 pairs of O's. So we have 2 pairs of N for every 4 pairs of O. Once again, a 2 to 4 ratio. All we've done is added in the word pairs. Scale it up to a dozen. If I have 2 dozen N atoms, which I have in this row here, if I count them up, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 N atoms. And another 12 N atoms. That gives us a total of 24 N atoms, which is how many dozen? 2 dozen. Can you guess how many dozen O's you will have? You will have 4 dozen because it is a 2 to 4 ratio, and 2 N's for every O, 4, 2 N's for every 4 O's. And we can count them if we want to. We can be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 1 dozen, 2 dozen, 3 dozen, 4 dozen if we count across the rows. So there are 4 dozen O atoms. So again, what's the ratio? 2 to 4. So what's the ratio if we have moles? The ratio is 2 to 4, right? 2 moles of N atoms for every 4 moles of O atoms. Now, I'm going to move this over a little bit. Let's see what I can do with this. Bigger. There we go. So we have the compound C2Cl6. And I know it's written right there, but if we had to, if it wasn't written there, could we write the mole ratio for carbon atoms to chloride atoms? So carbon atoms, and I don't just want chloride atoms, I want the mole ratio, so I want moles of carbon atoms to moles of chloride atoms. Take a look at the formula and tell your partner what number goes on the top and what number goes on the bottom. Two goes on the top. What goes on the bottom? 6. Now, sometimes people ask me, can I simplify that to a 1-to-3 ratio? Yes, you can, but we don't usually bother. Usually whatever's in the formula, we just go with that and stick it in our calculator as is. If you want to simplify it, though, it's certainly correct, okay? What would be the ratio for the moles of, why is my pen not working? That one. For the moles of carbon atoms, because we're doing the mole ratio here, to the moles of C2CL6 molecules. Tell your partner what numbers go on the top and the bottom there. Well, if we have one of these particles, how many carbon atoms would we have? We would have 2. So if I have 1 mole of those particles, I will have 2 moles of carbon atoms. Okay, so it's a 2-to-1 ratio. Okay, we're going to actually just skip ahead right now to page 29. And we're going to do question 1 together. And you'll notice that we have moles of iodide ions. That's our unknown. How many moles of iodide, I minus ions, are in, and our initial quantity is 2.5, our initial quantity is 2.50 moles of copper 2 iodide. See if you can write the formula for copper 2 iodide. What charge is copper? 2. Guess what? Copper 2 has a charge of 2. Iodine is a halogen, so it's in group 17. What's its charge? -1. So what is the formula for copper 2 iodide? CuI2, because we need 2 iodides to make -2 to balance out the +2. So we have 2.50 moles of CuI2. Now, if I have moles of one particle and moles of another particle, I can use the mole ratio to convert between those two. So if I have moles of A, particle A, and I have moles of particle B, I can use the mole ratio to convert between those two in one step. So our unknown, how many moles of I minus ions is equal to our initial quantity, which is the 2.50 moles of CuI2. And I know I can convert between moles of one thing and moles of another by using the mole ratio. So this is only going to be a one-step problem. What unit needs to go on the bottom so I can cancel? Moles of CuI2. And what unit goes on the top? Moles of I minus ions, because that's what we want to find. Tell your partner what numbers go on the top and the bottom. What number goes on the top? 2. And what number goes on the bottom? 1. So now we have 2.50 times 2, which gives us 5. How many sig figs should we have? We should have 3 sig figs, because here we have 3 sig figs. Mole ratios, because they're like, you know, counting atoms, it's the same as a particle ratio. Those are exact numbers, so these are exact. And so they're infinite. So we need 3 sig figs, so we're going to add a 0.00, and our unit is the moles of I minus ions. Okay? And you guys are going to practice that for a little bit by doing pages 26 and 27. All right? I'm going to come around and just like check your work as you go to make sure you're showing everything correctly. Hi. Yes. Yeah.
Chemistry 11
Yeah.
game. So I asked if I can just do chem talk and then take them. But she said it's kind of hard because I have to study on my own.
Yeah.
So I'm just thinking to study on my own. And is there anything like resources that I can get? I mean, if you have for the oh, is that like all English?
Yeah. But I haven't got unit 8, 10, or 8, 12, 8, 11, and 12 are not there yet. So there's 3 units, and then there's 3 more units.
How many? So there's like 6.
6 extra units.
Thank you so much.
Yes. What you have to remember is that when they start with unit 5. Right? So the moles that we're starting now, that's what they do like at the beginning of the semester. The 11 enriched people, they start with the mole. Because they have done all units 1 through 4 over the summer by themselves. Well, but you already know 1 to 4 periods. All right. Yeah, you've already done 1 to 4. You won't have to do 5, 6, and 7 because we're going to cover those ones. Okay, but like 8 through 13. Yep. Okay. Yeah. not that long. things. The homework on the board is going to be what's for homework. Like, if you want to do it tonight, you can do it tonight, but you can also do it after the test on Thursday. So this is like the homework for like this due on Friday. Yes? This homework is for today, but it's due on Friday because your test is tomorrow. So I'm assuming tonight you're going to be studying for your test. Yes? Yes, we're actually going to watch the video. Well, that's what we want to do. Tomorrow's test, there are 22 write the names. There are 22 write the formulas. So that's like one long page on each side. And then there's the chromatography stuff and the typing stuff. And so that's just like one page on either side. You don't have to. It's like optional. Yeah. Okay. Sure. Yeah. Yes. Yeah. Okay, cool. Thank you. All right, my friends, we are going to press pause on this, and we're going to spend a little time with Tyler. I think we're on page 30. Let me just check. We are on page 34. 34. Okay. So if you are doing math, put your math away. If you're on your phone, put your phone away. Because we're actually going to be covering a huge concept right now. Page 34. This is a vital concept to understanding the mole. Okay. Here we go.
In this video, we're going to look at how we can use moles to count the number of atoms we have in something. So, for example, here I've got a container with a bunch of chunks of carbon in it. I want to know how many carbon atoms do I have here? We'll learn how to figure that out here. So, just a quick review of moles. A mole is kind of like a dozen, except there are 12 things in a dozen, and there are 602 hexillion things in a mole, and we often abbreviate this number in scientific notation as 6.02 times 10 to the 23rd. Now, let's take a look at a mole. Right here, I have a mole of sulfur atoms, which is just about 602 hexillion sulfur atoms. Now, this is pretty crazy because it's such a giant number of sulfur atoms. Here's my question. How do I know that there are 602 hexillion sulfur atoms here, right? I couldn't count them out for two reasons. One, atoms are way too tiny, right? We can't even see them with a very powerful microscope. So there's no way that I could have seen the atoms and counted them out. Second of all, even if I could count out the sulfur atoms, there are so many things in a mole that it would take 20 quadrillion years to count from 0 up to a mole. So even if I could see these atoms, there's no way I could count them out. Yet I'm pretty confident that there are pretty close to 602 hexillion sulfur atoms here. How do I know that? Well, we're going to learn more about this. But it turns out that I can figure out how much a mole, 602 hexillion sulfur atoms, weigh. And then I can put this thing on a scale and weigh out that number of sulfur atoms. Let's talk a little bit more about this so it makes a little bit more sense. Okay, so here's an analogy. Let's say that I work at a candy factory, and when someone places an order, it's my job to count out all the pieces of candy that they ordered. Okay? One day, a giant rush job comes in for 10,000 jelly beans, and the person who placed this order wants exactly 10,000 jelly beans. What a pain this is going to be, right? I got a 1, 2, 3, counting out 10,000 jelly beans. It's not going to take all day. What could make my life a whole lot easier? Well, one thing that would be really awesome is if I knew how much 10,000 jelly beans weighs. Right? So what if I figured out that 10,000 jelly beans weigh 27,130 grams? That would be really awesome, because then all I would have to do is put a big bag on a scale and just shovel the jelly beans in until I got 27,130 grams of them. So in other words, instead of having to count, if I know how much 10,000 jelly beans weigh, all I gotta do is weigh out that amount. We can do the exact same thing here with moles. I told you there's about 602 hexillion sulfur atoms here. Of course I didn't count that out. That's because I know that 602 hexillion sulfur atoms, a mole of sulfur atoms, weighs just about 32.07 grams. So all I got to do is put this container on a scale, weigh out 32.07 grams, and I know I have just about 602 hexillion of them. So how did I know that a mole of sulfur atoms weighed 32.07 grams? Well, all you got to do is look at the periodic table. If I look sulfur up on the periodic table, I've got the element name and the abbreviation and stuff, and then I got this number down here. This is what we call the molar mass. And this number down here tells us how much one mole of this element weighs in grams. So
Okay, so have you guys seen this number before? 32.07 for sulfur. Grab your periodic table. Now yours probably just says 32.1, but what have we been calling that number? That's the atomic mass. And in fact, if we have one atom of sulfur, that has a mass of 32.07. What's the unit here? One single atom. The unit would be AMU. But if I have 6.02 times 10 to the 23 sulfur atoms, that's going to have a mass. The number is still 32.07, but what's my unit now? Grams. So in other words, 1 mole of sulfur atoms has a mass of 32.07 grams. And in fact, the reason that we chose the number 6.02 times 10 to the 23 is so that we could say that many grams is going to equal 1 mole, and that's going to be the same number as AMU. So we're basically scaling up from AMU to grams. And it's not a nice scaling factor like, oh, a gram is 1,000 times bigger than an AMU. A gram is actually 6.02 times 10 to the 23 times bigger than an AMU. Okay? And if you're like, that didn't make any sense to me, don't worry, you don't actually have to understand that scaling factor. But as long as you know that we have our molar mass, the mass of 1 mole, is the same number as the atomic mass. The only thing that's different is the units, but the number is the same. So the mass of 1 mole of sulfur, 32.07 grams. The mass of 1 atom of sulfur, 32.07 AMU.
32.07 is how much 1 mole 602 hexillion sulfur atoms weighs. Now, let's go back to the candy factory. Imagine that I get all kind of orders for all sorts of different candies. I can figure out what 10,000 of many different types of candies weigh. So, for example, maybe I have to do M&Ms one day, and I can find out that 10,000 M&Ms weigh 8,770 grams. They weigh less because one M&M is much lighter than one jelly bean, so 10,000 of them are going to weigh less. On the other hand, a candy like one of these chocolate molten balls, very delicious, are a bunch heavier than the jelly beans, so 10,000 molten balls are going to weigh a bunch more, 154,600 grams. So it's the same way with atoms. Some are lighter and some are heavier. So carbon, for example, is a little bit lighter than sulfur, and 602 hexillion carbon atoms only weigh about 12.01 grams because carbon atoms are just lighter than sulfur atoms. On the other hand, something like zinc atoms are heavier than sulfur atoms. So 602 hexillion zinc atoms, a mole of zinc atoms, weighs 65.38 grams. And just as I did with sulfur, I know how much the carbon and zinc moles weigh because I can look up the atoms on the periodic table. So here we got carbon, 12.01 is its molar mass, that's how much 1 mole weighs. And zinc, look that up on the periodic table, 65.38, and that tells me how much 1 mole of zinc, 602 hexillion zinc atoms weigh. So, if I want 602 hexillion, 1 mole, of any kind of atom, all I gotta do is look on the periodic table and find out how much a mole of that atom weighs. And then I don't have to count any atoms. All I have to do is just weigh out this amount on a scale. This is just like me being lazy in the candy factory. I don't want to have to count out these jelly beans or M&Ms, so I can just weigh them instead. I can do all my counting by weighing. And that's what I do with these atoms. I count by weighing out their molar masses. So, now that we know how to figure out how much a mole of atoms weighs, let's go back to that original question that I asked at the beginning of the video. I have here in this container a whole bunch of carbon. I want to know how many atoms of carbon are in here. Let's see how we'll answer this. Okay, so how many atoms of carbon do I have in this container? Well, let's think about moles of carbon. I look up carbon on the periodic table, and I find out that 1 mole weighs 12.01 grams. And I also know that in that 1 mole, there are 602 hexillion atoms. So the first thing I want to know is how many moles of carbon do I have? In order to figure that out, we can do some weighing, all right? I know that 1 mole weighs 12.01 grams, so let's weigh this and figure out how many total moles we have.
So he's going to put that carbon on a scale, and let's see how much that little container of carbon weighs.
I put this on the scale and find out that there are 31.87 grams of carbon atoms.
Do you have a mole of carbon? Do you have less than a mole? Or do you have more than a mole? Tell your partner. 31.87 grams of carbon atoms. Is that a mole? Is it more than a mole? Or is it less than a mole? How much does 1 mole of carbon weigh? 12 grams. So if I have 31 grams, do I have more than a mole, the same as a mole, or less than a mole? More than a mole. So we have more than a mole. We've got almost 3 moles, but not quite, okay? So let's see how much we have.
Here, now that's more than a mole. If we had 12.01 grams of carbon, we'd have 1 mole, but we have more than that. So let's figure out how many total moles we have. We'll do that by taking 31.87 grams, the total mass of carbon atoms here, and divide that by 12.01 grams, which is how much 1 mole weighs. And when we do that, we get 2.654 moles. So that is how many moles of carbon I have in here. Okay, We'll take this number, hold on to it, because it's going to be important for what we do next. Okay, so how many atoms of carbon do I have?
And actually, I don't like how he does this because he leaves out the conversion factor part. So we're going to go here and carry on if I can make it move. Oh, there we go. Okay. So here we are. Remember, we had 2.654 moles of carbon atoms. And we're going to multiply that by 602 hexillion carbon atoms for every 1 mole. Yeah? So now our moles cancel out. All right, but we're not going to write it out this way all the time because that's ridiculous. So instead of writing 602,000,000,000,000, we're going to write 6.02 times 10 to the 23 atoms per 1 mole. The moles cancel out, and we get, let's see what we get, 2.654 times 6.02 E23 equals, and I get 1.597708 times 10 to the 24. We have 4 sig figs here in the 2.654, but we have 3 sig figs in 6.02, so our answer will get rounded to 3 sig figs, and because that number to the right is a 7, we're going to round up to 1.60, and it's going to be times 10 to the 24. And the only unit we have left is the atoms, specifically carbon atoms. And if you want to know how many that is, that's it all written out. Okay? So that's it for today's lesson. This, like I said, this homework, I'm not expecting you to do it tonight. I'm expecting you to study for your test tonight, but if you're all ready for your test, you can get it out of the way. Okay, so this will be for like Thursday evening, but I figured if I told you during the test, you would never remember it. Am I correct? I feel like I'm correct.
to apply a program for next year.
Yes.
It's about early childhood education.
Oh, cool.
Yeah, and then I need a reference.
Reference? Okay.
And then I'm wondering if you can
Oh, sure, absolutely.
some questions.
Yeah. Yeah, so do I get that sheet of paper?
Yeah, sure. I'm thinking just taking.
Yeah, you can just take the staple out, yeah. And you can re-staple it if you want to without that in it, yeah.